This is an addendum to an earlier section, namely functions and relations. So in this video we are concerned with the absolute value function. So we're gonna define it and we're gonna derive some properties that pertain to it. Alright, so let's start. Let's start by defining the absolute value function. So let x be a real number. The absolute value of x, so I'm defining the phrase absolute value of x, denoted by 2 bars and x is sitting in the 2 vertical bars and x is sitting in the middle. This is just the symbol that represents the absolute value of x. And what does it mean? Well, probably the way you've seen it before is that it's the distance separating x, the value x, from the origin on the number line, right? So if this is the number line, one more time, so if this is the number line and that's 0, so wherever x is, if it's here, then we are talking about this as being the distance, correct? And if the point x is here, then this would be the distance separating the value x from the origin on the number line. And keep in mind, when we say the distance, we are talking about a non-negative entity, right? A distance cannot be negative. The least it gets is 0. Alright, so this definition that you've seen before, that you've probably seen before, is of geometric flavor. Okay, so the way we're gonna define it here, it's gonna be more of a pronounced algebraical nature. Okay, so we're gonna have an equivalent definition that's algebraic to this geometric definition. Alright, so the absolute value of x, denoted by this, is defined by the following. So let's see. The absolute value of x is defined by 2 things based on what x is, right? So if x is on this side, if this is where x is, the distance, let me just clean this part. So the distance separating x from 0 is this one, which is simply x, right? So this is then x if x is to the right of 0 or 0 itself. So if x is non-negative, right? And what happens if x is negative? So what happens if x is over here? So if x is negative, which means it's to the left of 0, well, I'm talking about this as being the distance separating 0 from x, right? Okay, so how can I represent this distance in terms of x? Well, this distance here is the same as this distance, correct? And what is this guy if this guy is x? This would be the opposite of that x. So this would be negative x. And as such, negative x is positive if x is negative, right? And according to the picture, x is negative. So negative x becomes positive, and this distance is that negative x, right? And hence this distance is negative x. Make sense? So what we're gonna define the absolute value of x to be when x is negative, it's gonna be just simply negative x. Okay, as we saw here. So one more time. Algebraically, what does the absolute value of x mean? Well, depending on the x, if x is non-negative, the absolute value of x is simply x itself. And if x is negative, the absolute value of x is negative x. Okay, it's the opposite of the guy sitting in between the bars. All right, these type of functions are called piecewise defined functions because they are defined based on other functions where collectively they make up this function. Okay, for example, the absolute value of x is defined based on the function f of x equals x, and the function g of x equals negative x. Based on what condition is verified, the sub-function is going to be activated. Okay, so for those of you who have done some programming, this is like the following. The absolute value of x is, if you want to write it in programming language, if x is bigger than or equal to 0, then this guy, the absolute value of x is x. Otherwise, or else, meaning if x is less than 0, the absolute value of x is negative x. Okay, so, and clearly these two conditions are complemental, right? This condition and this condition, but in the sense that they complement each other. Okay, so there is one and only one of the two conditions that's gonna be verified, and hence one and only one of these two sub-functions that's gonna be activated. Okay, all right, so let's see this definition in action. Let's consider the following example. So find the absolute value of, let's say, 5. Okay, well, so who's x in this context? Let's highlight this. The x is the guy sitting between the bars, right? So whoever sits between the bars is the x. So clearly that's going to be 5 then. Let's color this in purple. And as such, because x is 5, x is 5. So the idea is whichever condition is verified, the corresponding function is going to be activated, or subfunction. So x is 5. Which condition is verified? This one or that one? Is 5 greater than or equal to 0? Yes, 5 is greater than or equal to 0. So that's the one that's going to be activated, or that's the one that's going to be verified. This is the recipe of the output, right? That's the subfunction that's going to manufacture the output. Okay? So clearly this is not going to be verified. We just said it. They are complemental. So whenever one is verified, the other is not. So, long story short, absolute value of 5, since this is the condition that's verified, that's the function that's going to be activated. The output is simply, the output meaning the absolute value of x, or the absolute value of 5, is simply the x, and the x happens to be 5 here, right? So the answer is 5. Okay? So the absolute value function, technically in this case, when x is non-negative, does nothing. It keeps the output remains the input. The only time that the absolute value function does something to the input is when the input is negative. It multiplies it by -1 or takes the opposite of it. Okay, let's take another example. How about now we consider absolute value of -4. Okay, so again, let's erase this part and try to understand. Let's try to understand who x is. Well, as we said, x is the guy that sits between the bars. Who's the guy sitting between the bars now? It's -4. Okay, so x is -4, we know that. And now the question is this one or that one that, is this condition or that condition that's going to be verified? Well, x being -4 means that this is the one that's going to be verified because -4, the x is less than 0. Okay? As such, that's the recipe of the output. Keep in mind the x is -4. So the recipe of the output then is the opposite of the input, right? This is what it means. So it's going to be the opposite of the input. And who's the input? The input is x, which is -4. Okay? So what do we get at the end of the day? We get that this is equal to 4, because the opposite of 4 is simply 4. Okay, I hope this makes sense. Let's do couple more. How about now we take the absolute value of 0? Well, who's the x? The x is everything in between the bars, so it's gonna be just 0. And as such, since x is 0, as we previously discussed, one of the two conditions is going to be verified. Clearly, this is not the one that's going to be verified because 0 is not smaller than itself. 0 is bigger than or equal to itself, right? So that's the one that's going to be verified, and hence that's the recipe of the output. So who's the output then? Is simply the input, correct? So it's simply the input, which is 0. All right, let's keep going. So how about now I leave you with a question that we will discuss during class, and let's say that this question is as follows. Write the following expression without absolute values or absolute value. Okay, and the expression is absolute value of 3 minus pi. Okay, so the question is find this value without the absolute value. So we want to rewrite this expression without the absolute value. So the question is, what is it? Okay, all right, so I'm going to keep it here. Very good. So now let's keep going. So for those of you who forgot what pi is an irrational number, meaning it has decimal points which never end, and we do not have they don't behave in a regular fashion. Okay, so and pi is approximately 3.14. Okay, so think about pi as a number that's approximately 3.14. It's not 3.14, but it's bigger than this, but it's approximately this much. Okay. All right, so let's keep going, and let me consider the following problem. So exercise. Let's graph the following. Part 1, f of x equals x. Let's graph this function. So take a moment to do it. This is a linear function, right? Because it's of the form mx plus b. Remember this, mx plus b. So the m happens to be 1 in this case, and the b happens to be 0. So the slope of the line is 1, and the y-intercept is just the origin, right? Okay. So what you get is that, so this is the xy plane. Actually, let me just copy this because I need it shortly. Okay. All right. So the function is going to be just the line that's going to go through the origin, and it's going to bisect the first and third quadrants, right? Quadrant 1 and quadrant 3. It's going to bisect it, meaning the angle here and the angle here are going to be the same. Likewise here and here, right? Okay, so that's the line y equals x. Okay, so that's the function f of x equals x. All right, now let me add an additional assumption on the x. So I want you to graph f of x equals x, but only for those x which are greater than or equal to 0. So I wanna consider the function f of x equals x just for those inputs, right? X is the input. For those inputs that are non-negative. So meaning, go to this graph and retain all the points on the graph whose first coordinate is a non-negative. Remember, any point on this graph looks like x comma f of x, right? But f of x happens to be x as well. So here x comma x then. Each point has two coordinates, x comma x. They are the same, right? The y value and the x value are the same. So what I'm gonna do is I'm gonna go and keep all those points whose first coordinates are non-negative. Where are these points? So such a point, for example, has first coordinate. This is the x in this context, and this coordinate is clearly negative. So such a point should be erased, correct? So this point I'm not gonna retain. Likewise this point, because the first coordinate of this point is also negative. So all these points are gonna be erased, right? All these points. Where is the first point on the purple line that's gonna be retained? Well, that's the first point that's gonna be retained. Why? Because this point has coordinates 0, 0. And pay attention to the first coordinate. It's the x coordinate. It's 0, right? And 0 is greater than or equal to 0. So this point makes this condition valid. As such, I'm going to keep it. Okay? And any point after that is going to also be kept because such a point has a positive input. This is a positive entity. It's to the right side, or yeah, to the right side of the origin here, right? So this this point certainly has positive. This number is positive, and hence this point has a positive first coordinate. So I'm gonna keep it because it verifies this condition. Okay. So I'm gonna technically just eliminate this purple piece, right? All right. So let me erase all these red or orange marks. So as promised, I'm gonna only keep this point onward, right? I'm gonna erase everything else. And I'm gonna erase from here down. Make sense? Okay, let me just clean it a little more. Okay. Alright, so this guy is then the function f of x. Okay? Alright. Now, let's now part 2 of this problem. So part 2 of this exercise. Let me paste that picture that I just had before. Now what I'm gonna do is I'm gonna ask you to, I'll take it a little down. I'm gonna ask you to graph the function g of x to equal negative x. Okay? This is also a line. This is a descending line because the slope here is -1, but still the y-intercept is the origin. So what you're gonna get is, it's gonna be this line now that's gonna bisect the second and fourth quadrants, right? So this is the line y equals -x. Okay. All right. It has to go through the origin. So here it's not going through. It's almost there, right? But just with a grain of salt, just keep it. Think about it as crossing the origin. Now, what if I add to this question that I want you to graph this guy for those inputs, so for those x which are only negative? Okay, so now you're gonna restrict the function, the pink graph, you're gonna restrict it to those inputs which are negative. So you're gonna go to this line, which is to this graph, which is made up of points. Each point has coordinates, right? You're gonna only retain those points whose first coordinates are negative. So such a point here, its first coordinate, every point here looks like x g of x, right? Which is x negative x. But what's the first coordinate here? The first coordinate here is negative, is positive, right? That's the x, that's positive. So should I keep it? No, because this x, this first coordinate, doesn't verify the condition on my restricted domain, right? This is a restricted domain because I'm restricting. G technically accept everything, right? I'm restricting what it should accept. I'm forcing it to only accept negative numbers. So such a point should be eliminated from the picture because the x is the first coordinate is positive. Likewise, this point should be eliminated. So all these points here below the x-axis are going to be eliminated. Now, what should I keep? Should I keep this point? Yeah, this point has, don't forget, each point here is made up of two coordinates, x, g of x, but g of x is negative x. And the first coordinate here, which is x, is negative, right? So it verifies this condition. So this green point here is gonna be retained. Okay, so it looks like all these are gonna be retained. And where should I start erasing then? Well, pay attention to the origin. This point has two coordinates, 0, negative 0, but negative 0 is 0. Why negative 0? Because g of 0 is negative 0, but negative 0 is 0. 0 is neutral, it doesn't have a sign. So 0, 0. So that's the x then, correct? So that's the x. So should I keep this point? Well, don't forget, I'm only keeping those points whose first coordinates are negative. Is this coordinate negative? No, this is 0. So this green dot would be the last dot, or actually the first dot that should be erased if you move from left to right, right? So you're gonna erase all this piece. So all this piece should be erased. Okay. So you're gonna only keep this part. So let's do that. Let me actually first just take back everything I wrote in green. Okay. All right. So we said we're gonna erase everything here, right? I'm gonna erase everything here, and we're gonna only keep the part that corresponds to negative inputs. So 0, 0 is the last one that we need to erase, right? So we're gonna erase all of this. Okay, all of this should be erased. And even 0, 0 is gonna be erased because 0, 0, as we said, doesn't verify this condition. So if you erase this guy, right? If you erase this guy, what's gonna happen is you're gonna have a hole here, right? So you're gonna have a hole here. Hole means that the function doesn't reach the point, right? So the function is actually all these pink points, but you can get to the origin as close as you want, but the function is not gonna reach it, because once it reaches it, it gets to the point x equals 0, and such a point should not be, or apparently is not part of the graph. Okay. All right. So this is then the g function, the pink one. It has a hole, and this is the f function, the function f, which is the collection of all these purple points. All right, so let me make this smaller and actually move it to the middle here. Okay. And now here's the question. Let's zoom out and go back to the absolute value function. What's the absolute value again? The absolute value function is the absolute value of x is x if x is non-negative, and it's negative x if x is negative. So who's this function? Do you recognize this function here? It's this guy, right? So this guy is the function f below. So it has this purple graph. So this function has the purple graph. And now, who's this function? Right there. This function, when x is negative, this function is g of x. So it has this pink graph. Correct? So who's the absolute value function then? It's both of these. It's the purple and the pink, right? So one more time, the absolute value function, which was made up of this function and this function, but this function here has this as its graph. We just discussed it. And this function here has this pink graph as its graph. So collectively, the purple and the pink, collectively, if you plot them on the same xy coordinate system, you're gonna get the absolute value function. Make sense? Alright, so out of this discussion, then, we can say that, so it follows that the absolute value function has the following graph. Now what's the graph again? It's those two functions plotted on the same Cartesian system, right? So if this is the xy plane, the pink graph is this guy, say, with the hole, right? With the hole, don't forget. So this is the line y equals negative x. And the purple graph, the purple has a disk, not a circle, not a hole. It has this point is part of the graph. So if you take this line and you carry it all the way here, this hole is gonna be filled now, right? And you're gonna get a line like this. Okay, so that's the line y equals x. So the function has no holes, right? The function absolute value of x has no holes. It's continuous in some sense, right? Continuous in the sense that you don't lift up the pencil from the paper, right? So this is continuous, and as such, you do not have to explicitly just graph the bullet. You can simply just graph it as any other point. Okay, so what I'm gonna do is I'm gonna just adjust it, make it more natural. Okay, so let's continue this. Okay, it's gonna look ugly now. Let's just clean it. Okay. So one more time. If this is the xy plane, then we had the pink, and we had, so this is y equals negative x, and we had the purple, right? And this is y equals x. Okay, and realize that here I just graph this bullet as any other point. Okay. All right, so the collection of these two pieces is what makes the absolute value function. Okay, so who's the absolute value function then? Is those two branches. Okay, just a comment here. Are these two lines perpendicular? So is this angle 90 degrees? Well, what's the algebraic characterization of two lines being perpendicular? It means that the product of their slopes is -1. The slope of this is 1, and the slope of this is -1. So what's the product between -1 and 1 is -1. And as such, this angle is indeed 90 degrees. Probably it's not reflected here, but that's the case. This is 90 degrees. Okay. All right, so this is the absolute value function then. All right. Let's now take a horizontal line whose height is, let's say, 3. Okay. So let's take the line y equals 3. Don't forget the pink and the purple, these two pieces collectively, they make up the absolute value function. Okay, so here's the question then: when is the absolute value function intersecting this horizontal line y equals 3? Meaning at what points? So the question is, what are these guys? Apparently I'm gonna have two of them, right? So what are these guys? What are the x coordinates of these points? All right, let's pay attention. So this point here has two coordinates, right? So on one hand, the two coordinates are the same because this point belongs to the purple line, and any point on the purple line has the x and the y the same. The x coordinate and the y coordinate the same. So on one hand, I know that this guy and this guy are the same because the point is on the purple graph. And on the other hand, it also belongs to the orange graph. And the orange graph has the collection of all points whose y coordinate is 3. Okay, so again, one more time. This point on one hand is on the purple line, which means its y coordinate and x coordinate coincide. And on the other hand, belongs to the red or orange line, which means the y coordinate is 3. So the y and x are the same, and the y is 3, so both of them are 3, right? So both of them are 3. Does this make sense? So this guy is 3. Okay. All right, so we're gonna play the same game here. Same thing. This point belongs to the pink graph, which means the x and y coordinates are almost the same up to a change of sign, right? They're almost the same up to a change of sign. But this point also belongs to the orange graph, and the orange graph has all the points whose y coordinate is 3. So the y coordinate is 3 for sure. And since the x and the y are almost the same up to a change of sign, this guy better be -3. Correct? So the y coordinate is the opposite of the x coordinate, because this is the x coordinate, which is -3. The opposite of -3 is 3. So this is correct. So what's this guy then? The x coordinate is -3. Okay? Very good. So if I ask you now the question, if I ask you the following question, for what x, or find all the x for which the absolute value of x is equal to 3. Well, that's what we were doing, right? So we were talking about the absolute value function, which is the purple and the pink, the absolute value function to match the line y equals 3, the function y equals 3, which is the orange line. So the question is, what are the x coordinates of the points of intersection between the absolute value function and the function y equals 3? And we found them. They are plus and minus 3, right? Those are the intersection points, and the x coordinates of those intersection points happen to be -3 and 3. Okay? So we found that the absolute value of x equals 3 is equivalent to saying that x is plus or minus 3. That's what we found. Okay? Alright, so what if now I change the question to the following? What if now I change the question to the following? Instead of 3, how about b, a number b, where b is bigger than or equal to 0, obviously, because if b is less than 0, we're talking about the orange line then being translated all the way to the level here, right? This would be y equals b where b is negative, correct? And this is not the context that I'm working in. What I'm working in is the b, which was the 3, to be bigger than or equal to 0. Okay? So if this is the b, then what are these entities then? What are these entities? Well, this is gonna be bb then, right? And that's gonna be b then. This is gonna be negative b. I mean, it's the same treatment, but now we have an abstract number b, and that's gonna be negative b. Correct? So long story short, if we are trying to find all the x coordinates where this function, the absolute value function, and the function y equals b, where b is bigger than or equal to 0, that's the same as saying that x is plus or minus b. Correct? Do you agree with me? So there are 2 points that allow you to that are solutions technically to this equation. Absolute value of x equals b, that happens precisely when x is plus or minus b. And this is something that you've seen before, but I'm trying to explain it to you via the knowledge now that we have from this section. Okay? So let me summarize this result. Let me summarize this result. So I'm gonna write it here. I'm not gonna use the name x because it may be confusing in application. I'm gonna, instead of writing x, I'm gonna rename it to be capital A. So far we have the absolute value of a is equal to b, where b again is bigger than or equal to 0, right? That's equivalent to saying that a is plus or minus b. So this is a result I'm gonna keep. I'm gonna call it result number 1. I'm gonna keep, and I'm gonna derive more results for that pertain to inequalities, okay, not just equalities. So result number 1 is an effort to actually drop the bars, right? You have an absolute value equation on this side, and you have a regular equation on this side. So this is an effort to actually drop the bars. What does it take for me to drop the bars? It allows me to actually consider 2 equations. Either a is going to be b or a is minus b. Okay? So if you want to be just crystal clear what this means either a is negative b or a is plus b. Correct? This is what I was saying with this symbol, plus or minus. Okay. So now, if we ask the following question: find all x in R for which the absolute value of x is, let's say, less than or equal to 3. Okay? Less than or equal to 3. So I want all the x coordinates. I'm talking about geometry now. I mean, this is an algebraic question, but I'm gonna translate it geometrically, get information, and then go back to algebra. Find all the numbers for which the absolute value of x is less than or equal to 3. Geometrically, this means I want to find all the x coordinates of the point that belong to the graph of the absolute value function, which is this v-shaped function, right? That are below in terms of the y value of those points, that are below their corresponding points on the orange line, right? So in other words, where does the absolute value function or where is the absolute value function dominated by the red function, the orange function, because 3 is the orange function, right? Where is the v-shaped function dominated by the orange function? And by dominated, I mean that's below or at, right? Where is the v-shaped function below or at the orange function? Well, we're talking then about I mean, what is that thing? Where is the v-shaped function? The v-shaped function below or at the orange function? So at this point, they are at, right? So let me make it wider. So this is a point where they meet. So I have equality. We discussed this in the previous context. And this portion is a portion of the v-shaped function that's below the orange function, correct? It's that highlighted in green thing. So they meet at these blue dots, and this part of the v-shaped function is below the orange function, correct? So that's what we're talking about here. But I'm not talking about, I don't need all the x and y coordinates of these points. I only need the x coordinates of these points, right? So only the x coordinates of these points. So to which x coordinates this happen? Well, all these points have x coordinates that belong here, right? Have x coordinates that belong here. And the intersection points happen when x is -3 and x is 3, correct? Does it make sense? So, long story short, that thing happened, that type of inequality happens for all x's that are in this red region or red portion of the x-axis. So any x that's between -3 and 3, including -3 and 3, because at the endpoint I have equality, any point belonging to this portion of the x-axis is gonna verify this inequality, meaning its y-coordinate is gonna be on the y equals absolute value function, on the absolute value function, is gonna be smaller than or equal to its y-coordinate on the y equals 3 function, right? So what I'm saying explicitly is that for such a point, the y-coordinate, if this is x, the y-coordinate of this one through the function absolute value, I'm gonna get absolute value of x right there. This is the height absolute value of x. And for this input, under the function y equals 3, I'm gonna get this guy as the y-coordinate of this or the output of this input via the function y equals 3, right? So obviously this measure is bigger than this blue measure, right? So this is why this is correct. Okay. at the endpoints they meet each other, and anywhere in between you have a complete dominance. Okay, so anywhere in between you have that the absolute value function is lower strictly than that orange function. Okay, so how can we summarize this then? Let me actually erase all of these. So we understand now that any x between -3 and 3 does the job, right? All right. So what I'm gonna get is, this is then equivalent to saying that x is between -3 and 3, right? Any x between -3 and 3 is gonna do the job. Now there was nothing special about 3 here except that it's bigger than or equal to 0. So if you go for a b, instead, the same thing is gonna happen, right? The same thing is gonna happen. You want the x to be in between -b and b. Correct? So we get something like this. And we get the following result. I'm gonna write a similar result to part 1 here in pink. Instead of calling the variable x, just to eliminate ambiguity, I'm gonna call it a new variable a. It's just renaming the guy that's sitting between the bars. If you go for a for name, less than or equal to b, that's equivalent to the a is sitting between -b and b. Correct? So the absolute value of a is between b is less than or equal to b. This is the same thing as saying that the a itself, the guy under or in between the bars, is between -b and b. Okay, so again, this is an effort to transition from the left side to the right side of this equivalence of this statement. You can think about it as an effort to drop the bars. No bars here, right? No absolute value here. So this is what it takes for this inequality to translate into a regular inequality without absolute value. Okay. All right. And let me, since we're talking about it, so how about I add the following? If here we don't want equality, right? If you don't want this equality, which means you don't want the intersection between the two functions, the v-shaped function and the orange function, so you're not gonna allow the endpoints. You're not gonna allow the x to reach the endpoints. So you're gonna throw away the -3 and the 3. And the abstract context, you're gonna throw away the -b and the b. Correct? So because they only meet, they are equal. I'm talking about this equality. They are equal when x is plus or minus b. We talked about it in the first one. Okay? So what I'm gonna say is, if you have a strict inequality, meaning if this guy is not there, that's not gonna be there and it's not gonna be there, right? If you include the equality here, you gotta include it here and here. Okay? Alright, and the last part, the last result that I wanna show is, what if now I ask the following question? If I wanna find all real numbers for which the absolute value of those numbers is greater than or equal to b this time, right? So I want the absolute value function now to be dominating, or to dominate, you know what, let's keep the 3 just to keep it concrete first, and then we go for the abstract context. So again, I want all the real numbers for which their absolute value are bigger than or equal to 3. So geometrically, this means I want to see where this v-shaped function is dominating or equal the orange function, right? So let's go to the picture. Where is the v-shaped function dominating or meeting, intersecting the orange function? So we're talking about, this is where they meet again, right? And this portion of the v-shaped function actually dominates the orange. and this one as well, right? Agree with that? So these are the two branches of the v-shaped function that dominate the y equals 3 function, the horizontal line. And these are exactly where they meet. Okay? So to which x this corresponds to? To which x this corresponds to? Right? Because the question has to do with x. To which x this happens? Well, all these points, remember this means it keeps going up, right? It blows up this way and blows up this way. Well, all these points have those guys as their first coordinates, right? So any point on this branch has an x coordinate coming from here, and this point has its x coordinate being -3, correct? How about this branch? This branch, any point on this branch has its first coordinate in this portion of the x-axis, correct? Again, this keeps going up, so if you drop those points, you get those x values, right? Okay, and this intersection point is right there. It has this x coordinate, which is 3, as or this point as its first coordinate. Make sense? So if x lives in this brown area or brown portion, or in this brown portion, it's gonna produce an output via the v-shaped function bigger than 3 or equal to 3. Correct? So it's gonna be a solution to this inequality. All right. So any brown number is gonna be a solution to this inequality, right? Okay. So I'm gonna now put them in a set. All these brown elements, I'm gonna put them in a set. What are these guys? What are these guys? The brown guys. These are -infinity all the way to -3, right? Including -3 if you want equality. And how about these brown guys? These are from 3 onward, right? Now, if you wanna collect all the solutions to this inequality, so which means you wanna make a set that's made up of all these brown guys, so you're gonna take the union between this and this. Make sense? So any x that's at most -3 or that's at least 3 is gonna do the job. Okay, so this is exactly what I'm gonna write here. I'm gonna keep writing it using inequality. I'm not gonna use interval notation. I just wanted to say it just to follow suit with what we've been doing. So the absolute value of x being greater than or equal to 3 is equivalent. That's an absolute value inequality. If you want to drop the absolute value, that's the price to pay. X is less than or equal to -3, so it's at most -3. These would be those brown guys. Or x has to be 3 or more. So or x has to be 3 or more. Correct? Very good. So if you don't want to go for a specific number, obviously we would like to develop a result that encompasses a wide range of application. You don't want to go for a specific thing, right? How about going for a number b under the assumption that b is non-negative? So we're talking about these guys being b then, instead of 3 and -3. So the result becomes like this. So the absolute value of x greater than or equal to b is equivalent to saying x is less than or equal to -b or x is greater than or equal to b. Okay, and the corresponding pink result becomes the absolute value of a is greater than or equal to b. That's equivalent to saying that a is less than or equal to -b or a is greater than or equal to b. Okay, and as we discussed above, if you don't want this equality to happen, so meaning if you don't want the two graphs to intersect, then throw away the -b and b, the endpoints. So just eliminate this inequality and eliminate this inequality. Correct? So the absolute value of A is greater than B if and only if A is smaller than minus B or A is bigger than B. This is how I would read the statement if I eliminate the equalities. Okay? So in summary, let's summarize, or let's write all the results in one theorem. Let's call it a theorem. Let A and B be real numbers. Again, all these results should have been seen before, but now I'm making the connection with, since we know what a function is now, so I'm making the connection how these results were derived, or a way how these results were derived. So let A and B be real numbers such that B is greater than or equal to 0. Right? Because everything we discussed above was under the assumption that B is greater than or equal to 0. Then the following hold. Okay. Property 1. Actually, I'm gonna just copy them. So property 1 is this pink one, right? So I'm copying this. Let's keep it in black. Property 2 is this guy. Okay. So this would be property 2. Let's also keep it in black. And property 3 is this result, and let's also write it in black. Okay, so keep in mind obviously that those inequalities, if you go for, if you add this, you gotta add this and this, and if you add this one, you gotta add this one and this one, right? This is what we discovered along the way. All right, so let's take examples from the book. That's on page 148, and let's do 78, for example. So the question is, determine the x and y intercepts for the given function. So we've done something like this for other functions. We know what x and y intercepts by now. And let's do 78. So k of x is the negative absolute value of x plus 2. Okay? So this is page 148. And that's number 78. So the function is k of x equals minus absolute value of x plus 2. Okay? So we want to find the x-intercept. Remember, to find the x-intercept, we know that we need to solve the equation k of x equals 0. So the solutions of this equation would be the first coordinate of the x-intercept. The y-coordinate is certainly 0, right? Okay. K of x is equal to 0. That's exactly as, this is the same as saying minus the absolute value of x plus 2 is equal to 0. Because that's what k of x is, right? All right. So this is an absolute value equation. So in some sense or in some way, I need to invoke part 1 of the previous theorem. To set the stage, I need the absolute value by itself on one side and the other guy to be by itself, and I need this guy to be bigger than or equal to 0, right? I need this guy to be bigger than or equal to 0, because if it's negative, this equation has no solutions, right? Because the absolute value is at least 0. There's no way an absolute value function can reach a negative number. Okay, so this is why this condition, it's an overriding assumption. You cannot overlook it. Okay. All right. So to set the stage for this, I mean, to put myself in this scenario, I need to isolate the absolute value and the other guy to the other side. So this is equivalent to saying minus absolute value equals minus 2, correct? This is by just subtracting both sides by -2. It's not there yet because this minus is not in this, this minus has no role in this setup, correct? So I need to get rid of this minus, so I put myself in this setup, and to do so just multiply both sides by -1 or divide by -1. You get absolute value of x is equal to 2. Okay, so now this format is the same as this setup. Now I know who A is and who B is. So who's A in my context? A is the x then. That's the A here. And who's the B? That's the B. Correct? That's the B. And is the B bigger than or equal to 0? Is the B bigger than or equal to 0? Yes, the B is 2. Certainly is bigger than or equal to 0. So as such, I can employ this result. It's going to allow me to transition from an absolute value equation to a non-absolute value equation, to an equation which is regular. Here I'm going to pick up two equations. It's going to be like a compound equation that's equivalent to this absolute value equation. Okay, so by part 1 above, we can write that part 1 says A is minus B or A is plus B, right? So A is x. So A is minus B, so minus 2, or A is plus B, so A, which is x, is plus B, which is plus 2. Okay? So these are the two x coordinates of the x-intercepts. Okay, so therefore, the x-intercepts are -2, 0 and 2, 0, right? Okay. All right, and now the y-intercept of this function. Well, the y-intercept is the point whose coordinates are 0, k of 0, right? So 0, k of 0, so it suffices now to evaluate k of 0. K of 0 is minus, who's playing the role of x here? It's the 0. So every time I see x, I'm going to have a 0. So I'm going to have absolute value of 0 plus 2. Okay, I'm following the recipe for the output through k. The input now is 0. Okay, and what's absolute value of 0? We discussed that before. That's 0. So minus 0 is 0, plus 2 is 2. Okay, so the y coordinate then, the y-intercept then is 0, k of 0, which is 0, 2, because k of 0 happened to be 2. Okay, alright, so let's go back to the book, and let's go to one of these problems from 97 to 110, and let's go to 106 part B. Okay, so let's do 106 part B. So we want to find the domain of the function g of a equals 5 divided by 8 minus the absolute value of a minus 2. Okay, so let's write this down. That's problem 106, and this is part B, we said. So we have g of a is equal to the quotient 5 divided by 8 minus the absolute value of a minus 2. Okay, so the question is, what's the domain of G? Well, we've done problems on this, or like this, but here the nature of the denominator is different. So recall the following: a quotient is meaningful, so n over d is meaningful, so it's a number, if and only if three things we talked about this in the other video, if and only if n itself exists and d also exists in their own rights, right? And lastly, the denominator is not 0. Okay, so these are the three conditions that allow a quotient to be meaningful. All right, so who's n and who's d in the context of 106? N is the 5, and d is this guy downstairs, right? That's d. Okay, so that's d. Okay, so in this context, when does the quotient exist? Well, it exists precisely when these three happen. For condition 1, what does it mean? Condition 1 means the numerator exists. So for what a, so here a denotes the input. So for what a, the numerator exists? Well, the numerator is independent of a, and it's a pure constant. So it's always existing. No matter what a is, the n, the numerator, is always meaningful. So n exists for all a, right? For all a real numbers, for any real number a. Okay, how about d? When does d exist? Look at d. It's 8 minus the absolute value of a minus 2. So is there any a for which d doesn't exist? Let's see how d is manufactured. You give an a to this denominator. What's gonna happen is you're gonna subtract 2 from the a. You can always subtract 2 from a real number. Okay, so you're gonna obtain this result. Once this result is obtained, you take the absolute value of it, and the absolute value exists for any real number based on the definition of the absolute value function discussed above. So this whole thing is gonna be meaningful for any a, and then once this is meaningful, you can subtract it from 8. Okay, so this process is smooth no matter what a is. So d exists for all real numbers a. Okay, so far conditions 1 and 2, this one here, this one here, and this one here, those two conditions allow any real numbers. So they don't put any restrictions on the real numbers, on the input a. Okay, so the only remaining part is the last part, which is the denominator not being 0, and the denominator is this guy. Okay, so the denominator is not 0 means, in the context of 106, it means that 8 minus the absolute value of a minus 2 is not 0, right? Okay. Alright, so the question becomes, what are the restrictions on a so that this doesn't happen? Or this guy is not 0. Okay. So the question again, when does this happen? For which a? So how about we try to actually solve this equation? And whichever solutions we get here, since we don't want solutions, we don't want this guy to be 0, I'm going to try to find when this guy is 0, and then throw away the a's, the solution of this equation. Okay, so this is clearly an absolute value equation. I have absolute value and I have equality, so this is an absolute value equation. And how do we handle it? Well, I'm going to appeal to the theorem that we just discussed above, so namely part 1. So I'm gonna set the stage for property 1 to kick in, the left side, the left statement. So I'm gonna have the absolute value by itself and the other guy on the other side, and if that guy b is non-negative, I can employ that property. Okay, alright, so let's set the stage. So I need the absolute value by itself on one side and the b on the other side. Well, this is the same thing as saying that the absolute value of a minus 2 is equal to 8. Do you agree with this? If you just move this guy to the other side, you get that the absolute value of a minus 2 is equal to 8. So you get this. And now based on property 1 above, let me take you there again. Actually, let's put both of them on the same screen if possible. Alright, so I want you to look at this, and actually look at this, and convince yourself that I am in the same setup. Okay, so I have absolute value of something on one side and b on the other side, which is 8 in this case, and b, I need b to be bigger than or equal to 0, right? This condition here. Well, b apparently is going to be 8, certainly is non-negative, and capital A in property 1 is going to be little a minus 2, right? So we're going to use property 1 above. So we're going to use property, so over here, I'm going to tell you the package that's going to go along here. So we're going to make use of property 1 with capital A in the property, as we discussed, is going to be little a minus 2, and capital B in the property to be 8, which is clearly non-negative, right? Which is clearly non-negative. As such, property 1 is applicable, and as such we get that capital A is going to be either minus B or capital A is plus B, right? And we have this dictionary. Capital A is little a minus 2 and capital B is 8. So I used this side of the statement because I transitioned from the absolute value part to the non-absolute value part, and I use the dictionary. Capital A is little a minus 2 and B is 8, so I get little a minus 2 is either minus 8 or it's plus 8, right? So this is what's written in blue here. Okay, so we transition from absolute value equation to a non-absolute value equation, and each one of these two equations here is simply a linear equation in two variables in one variable. So we can easily handle it. The first one, if you add 2 to both sides, you get that a is equal to minus 8 plus 2, so minus 6, or this means that also you add 2 to both sides, so a is 10, right? So either a is negative 6 or a is 10, and the solutions here, which are minus 6 and 10, are exactly the solution of this equation. Okay, now you did not want this to happen. You didn't want this or this equality or this equation to be true. So if you don't want it to be true, you don't want these guys, because the only time this statement or this equation is true is when a is minus 6 or a is 10. Okay, so this guy then, that's equivalent, because I want to negate this. If you don't want this to happen, so you don't want a to be negative 6 and you do not want a to be 10, right? Very good. So all this guy was needed to transition from this thing to this thing, right? Okay. Alright, so I'm gonna make it smaller so it can fit on this page, and I'm gonna do it right here. Very good. Alright, so what were you trying to do here? We were trying to find all the acceptable a's through the function g. According to this discussion, first condition brings no restrictions on a, second condition brings no restrictions on a, but the last condition brings these two restrictions on a. So at the end of the day, we get that. G of a is defined, correct, which is this quotient here, if and only if we took time to understand when this quotient exists, if and only if this happens. A is neither negative 6 and is neither minus 6 or 10, right? So it means that a should not be negative 6 and a should not be 10. Okay. Therefore, the domain of G is all real numbers except those guys. So I'm gonna throw away the set consisting of minus 6 and 10. So I'm gonna throw away this doubleton from all the real numbers, from the set of all real numbers. Again, don't forget, this is the same as saying minus infinity to minus 6, open, union minus 6 to 10, union 10 to infinity. Okay, so either you use interval notation or you use set theoretic difference. Okay, so these are all the acceptable A's. They belong here to this union that are acceptable by the function G. Alright, what if now I take the same question as above, but I tweak it? So what I'm gonna do is I'm gonna use a different color. So let's go for red. So I'm gonna call this guy B prime, and let's go for h of a to equal, let's go for 5 divided by the square root of 8 minus the absolute value of a minus 2. Okay, so very close to G, but downstairs now has an umbrella. Okay, alright, so I'm gonna employ this again because the nature of the recipe of the output of H is a quotient, and a quotient exists if and only if the numerator exists and the denominator exists and the denominator is not 0. Okay, alright, so let's take our time to understand what happens here. So h of a exists. It's the same treatment as above. If and only if 5 divided by the square root of 8 minus the absolute value of a minus 2 exists, and this guy here is a quotient, and again, a quotient exists if and only if these three happen. Okay, so if and only if the numerator exists, so 5 exists, and the denominator exists, so square root of 8 minus the absolute value of a minus 2 exists, and the denominator is not 0, right? So the denominator is not 0. Correct? So what have I used? I used this guy. Correct? So how about we copy it and let's actually inject it right here. Agree with that? So this is what happened. So I used this package to actually transition from here to here. Why? Because this is of the form n over d. It's of the form something over something else, and such a thing exists. That's the package I'm using. If and only if the numerator exists, the denominator exists, and the denominator is not 0. N, I'm using it to be 5. Capital D, I'm using it to be the square root of this entity here, right? Okay. Alright, so now back to understanding what conditions what demands each one places on A. Well, the first one doesn't place any demands on A because no matter what A is, 5 is always existing. Okay, so 5 exists for all real numbers A. Correct? The second condition, how about we call this entity or this statement here, how about we call it 2. Okay, so let's take 2 by itself and understand when this happens. So 2 is square root of 8 minus absolute value of a minus 2 to be meaningful. When this thing is meaningful, if and only if, what do you think? When is the square root of something meaningful? We talked about this before. Square root of something is meaningful if and only if that thing is 0 or more, right? We cannot put anything that's negative under the umbrella and claim that the umbrella, the whole thing, is a number, a real number. So that's what I'm gonna invoke here. So I'm gonna say I know exactly when the square root of something exists, and the thing here happens to be the thing under the umbrella happens to be this package, right? That's the capital A I'm using in this property. So for the square root of this guy to exist according to this result, this happens precisely when the guy A, so 8 minus absolute value of a minus 2, is greater than or equal to 0. Agree with this? One more time. Condition 2 here, I'm trying to unravel what it means in terms of A. What are the A's that allow this guy to exist? Well, this entity here, it looks like square root of something. And square root of something is meaningful if and only if the thing, the radicand, is greater than or equal to 0. This is an earlier result. We know this. So my radicand here happens to be 8 minus absolute value of a minus 2. So I need the a, so the 8 minus the absolute value of a minus 2, to be non-negative, and that's what it takes exactly for the square root of this entity to exist. Okay? Alright, so this becomes an absolute value inequality. So it looks like an absolute value inequality, and we do have properties that can handle that, right? Properties 2 or 3. It's one or the other, correct? So let's check which one. And to do so, I need to isolate the absolute value by itself and everything else to the other side. Okay, so this is equivalent to saying that a is greater than or equal to the absolute value of a minus 2, correct? If you move the absolute value to the other side, meaning you're adding that entity, so the absolute value is going to pop up here. 0 plus the absolute value becomes this. Okay? And now if you contrast this format with the result we have, both results, 2 and 3, have the absolute value on the left side, correct? Have the absolute value on the left side. So to understand which condition it is, we need to put the absolute value on the left side. Well, if something is greater than or equal to something else, then this something else is smaller than or equal to this thing, right? So this is equivalent to absolute value of a minus 2 less than or equal to 8. One more time. These two are the same because, just read it. If 8 is at least the absolute value of a minus 2, this means that the absolute value of a minus 2 is at most the 8. Okay, so they are the same. Okay, so now which one is it? It looks it's property 2. It's property 2. So property 2 says if you have such a thing, as long as b is non-negative, don't forget this, but the b here is 8, so it is non-negative. So you can rewrite, instead of having this inequality, you can have this compound inequality. So the a has to be sitting between minus b and b, and if you have less than or equal, here you're going to have less than or equal, and here you're going to have less than or equal. So I'm going to employ property 2 in my context with capital A to be little a minus 2 and the b to be 8. Okay? So here we're going to employ property 2 So we're gonna use property 2 above with capital A and property 2 to be little a minus 2 and capital B there to be here the 8, and clearly the B is non-negative, so as such I can use that property, right? Okay, so then what? Then we can write that the capital A, which is the a minus 2, should be sitting between the minus 8 and the 8. Correct? That's what property 2 is. Let me take you back there. It's right here. Correct? It's right here. So capital A has to be at least minus B and at most B. So since the capital A is little a minus 2, I'm gonna have that a minus 2 has to be between minus B, but B is 8, and B itself. Correct? And now what does this mean in terms of A? Well, if you add 2 to all sides, you're gonna have minus 8 plus 2 is minus 6, less than or equal to a minus 2 plus 2, so A, and 8 plus 2 is 10. Okay? So long story short, condition 2 exists precisely when A is between minus 6 and 10. Correct? So how are we gonna do it? So what I'm gonna do is I'm gonna call this Roman 2, and I'm gonna say that this is equivalent, so meaning this statement happens precisely by the discussion 2. Let's call this whole discussion here 2. That's equivalent to little a being between minus 6 and 10, possibly negative 6 and possibly 10. Correct? And that 2 is this discussion. Okay? Alright. Very good. So now the last part, let's give it also a name. How about we call it 3. So discussion 3, we're gonna do it below. When does the square root of 8 minus the absolute value of a minus 2 not 0? Well, condition or discussion 3. So the square root of 8 minus the absolute value of a minus 2 is not 0. This is exactly what we have, right? This is exactly what we have. Well, when is the square root of something equal to 0? Well, if you raise both sides to power 2, if you apply the squaring function to both sides, right? If you square both sides, you're gonna get this happens precisely when 8 minus the absolute value of a minus 2, when this is not 0, right? Because the only time the square root of something is 0 is when the thing, the radicand, is equal to 0. If you don't want this to happen, so you don't want the radicand to happen, the radicand to be 0. Okay, but we've done this before, right? We know exactly when this is 0. It was discussed, what is it? It was discussed right here. We know exactly when this is 0. It's 0 when a is minus 6 or a is 10. So this is from above, right? Discussion above. This is the same as saying that a is not negative 6 and a is not 10. Correct? Such equation is called radical equation. So an equation which involves square root is called radical equation. And if you'd like to revisit this concept, I have a video. Just go to my channel and search for radical equations, and you're gonna see a video on this. You don't have to watch the whole video, just see a couple of see the properties and a couple of applications. Okay, so you're gonna need something like this in problems 107, parts B and C. Okay, but we can still talk about it during class if you're still struggling with it. Okay, all right. So so we got our hands here, we finished this, and now let's finalize this part. By discussion 3 below, this happened to be equivalent to saying that A should neither be -6 and A should not be 10, right? So these are the conditions that we have from discussion 3. All right, let's put things together now. So at the end of the day, what do we have? H of A exists if and only if A is a real number, and I'm gonna box them for you. Okay, so I'm gonna box them for you. H of A exists if and only if, right? A is a real number, and A is between -6 and 10, including the endpoints, and A is neither that nor this, right? So putting things together, we can say that H of A exists if and only if A is a real number that's between -6 and 10, but do not equal those endpoints. Okay, so this would be, if you put things together, this is how you read it, and that's exactly what I'm gonna be doing next. So all in all, H of A is meaningful if and only if A is a real number such that A is between -6 and 10. Strictly taken between -6 and 10. Those endpoints by condition 3, by discussion 3, should not be there, right? So -6 and 10. So what's the domain then? So therefore the domain of H is the interval -6 to 10. Open, right? That's it. So by these 3 conditions, we can say that A should be between -6 and 10, excluding those endpoints. Okay? All right. So this was 106 part B, and we did the new one, B prime, we called it. Okay? Let's look at 106 part C. Take a look at part C. It's very close to part B, except I have a plus here instead of a minus, right? So I'm gonna discuss it. I'm gonna just discuss it. I'm not gonna write anything. I'm gonna discuss it and see what type of changes this change of sign is gonna make. Okay, so think about it. If we have a plus here, let's do it in a different color. How about purple? Okay, so if we do plus here instead, in 106, this is part C, right? If we change this to plus, well, what's gonna happen? N is gonna remain meaningful for all A. D is gonna exist, the new D is gonna exist also for all A, because the absolute value of A minus 2 happens to exist for all A, as we discussed before, and now instead of subtracting that result from 8, you're gonna add it to 8. So that still remains true for all A, right? But now the minus here is gonna become a plus, and then according to this discussion in blue, what's gonna happen? Let's zoom in so we can see exactly what's going on. So that's the plus then. And now if you move to set the stage for the condition, the property 1 that we talked about above, to kick in, you need the absolute value of a to equal a b, right? And for this setup now, you're gonna have a minus 8, correct? If you move the 8 to the other side, you're gonna have a minus 8. And now this b becomes minus 8, right? The b here becomes minus 8. And if you go back to property 1, this property now, it looks like I can apply it, but don't forget, see this b here? You can apply it as long as b is non-negative. Well, our b in this context is negative 8. In the new context, right? It's right there, it's negative 8. So I cannot use the property 1 that I just talked about, because the only time I can use property 1 or any of the properties 1 through 3 above is when b is non-negative, and that was a crucial condition, right? Otherwise I cannot. So now I am on my own, and I cannot appeal to that anymore. But take a look. The absolute value of a minus 2 is equal to minus 8. Well, what do you know about this guy? The least this guy gets is to 0, right? So this guy is at least 0 for all a. No matter what a is, the absolute value cannot be negative, right? So since this guy is 0 for all a, there is no a that makes this guy equal to a negative number. Okay? So one more time. Since the absolute value of anything is 0 or more, so absolute value of a minus 2 is at least 0 for all choices of a. As such, no matter what a is, that guy is gonna be at least 0, and hence there is no a that makes this entity equal to a negative number. Okay? So what can you say then? Condition D becomes, the condition that I'm trying to unravel here is this, but this can never happen. This is never 0, because if it were to equal 0, then absolute value of a minus 2 is going to be negative 8. And we just discussed this cannot happen, because no matter what the real number a is, those two are not the same. This guy is bigger than or equal to 0, and this is negative. So there is no a that makes 8 plus the absolute value of a minus 2 equal to 0. So instead of having this now, I'm going to have this happens for all real numbers a. So for all real numbers a, correct? Any real number makes 8 plus the absolute value of a minus 2 different than 0. Okay? Because this guy is at least 0. Adding 8 to an entity which is at least 0 is going to be at least 8. And hence there's no way I'm going to make this equal to 0. And this is discussed here. So putting things together then, for the new problem, the plus, this condition is bringing no constraints on a. This condition is bringing no conditions on a. And now this last condition is bringing no conditions on a. So putting things together, this quotient, so this quotient here is gonna be valid for all real numbers. So the domain of this function with the plus is gonna be all real numbers. Okay? Because these three conditions, none of them actually places any conditions on the a. I hope this makes sense, and that's gonna be the end of this addendum.